Chapter 23, Section 5 deals with energy in electromagnetic waves. All waves carry energy, so it's no surprise that electromagnetic waves, things like X-rays and microwaves, carry energy. We usually express that in either energy density or sometimes in terms of intensity. They're both related to energy, they're slightly different. Energy density has a lowercase u for its symbol, and it is energy per unit volume. You can think of the electromagnetic wave as taking up space in the air. So if we are in empty space, that's a vacuum, or air is almost empty space, then the energy density U is equal to 1/2 epsilon naught E squared plus 1/2 1 over mu naught B squared. Now, we can simplify this a little bit because we know that B is equal to E over C. And we know that C is equal to 1 over the square root epsilon naught u naught. So if I put this, I end up getting that. We can actually write that B, or in particular B squared, is epsilon naught mu naught E squared. If I plug that in there, then I get the energy density is 1/2 epsilon naught E squared plus 1 over, put that together, 2 mu naught epsilon naught mu naught E squared. And we see that this will cancel, and 1/2 plus 1/2 makes 1 whole. And we actually get a fairly simple expression that the energy density is just epsilon naught E squared. It has a unit, SI unit, of joules per cubic meter. Okay. Another way we sometimes think that's related to this idea of energy, it's not energy, is intensity. The intensity, which is sometimes expressed with an I and sometimes expressed with an S. So I'm going to put both. S is probably nicer because we use capital I for current, but actually I is the one that's somewhat intuitive. And intensity is the power per unit area. Our formula, if you think of this being per cubic meter, if we want it just to be per area, it comes out to look like I, which is the same thing as S, is equal to epsilon naught CE squared. Now the book will go through and derive that for you. It's just more fun with algebra. It has its units. Power per unit area means it's going to be watts per meter squared. We know that epsilon E squared is simply U, so another way we can write this is that the intensity is simply the speed of light, c, times the energy density. Again, it's the same unit. It's going to have units of watts per meter squared. Now, all of these formulas that we found so far, oh my goodness, I did not start with a blank page. We'll go sideways. All of these units that we have looked at so far are for an instantaneous value. So in the formulas we've looked at, E was the instantaneous value. Remember, E is sinusoidal. E is doing this. It's oscillating from its maximum to its minimum. Now, E squared is always going to be positive, but that's still going to be a changing value. The average power, intensity, energy, whatever you want to think about it, is found by replacing the value of E with 1/2 E max squared. So the average value uses half of the squared value. So if you think of squaring this and then halving it, what that means is the average intensity is epsilon naught C, and then instead of E, we're going to put E max squared over 2. You'll remember that if we do some substitute, or even simpler, here's my favorite. It's just C times the average energy density. It's one way of thinking about it. If we take this formula that we just had and we did some rearranging, we know that C is 1 over the square root of mu naught, epsilon naught. We know that E max is equal to C times B max. So I can say that it's equal to B max over mu naught epsilon naught. If we put this in for one of these, look what happens. Again, we're just sort of having fun with algebra. I get that the average intensity I've got epsilon naught. I'm going to replace that C with 1 over the square root of epsilon naught mu naught. And then I'm going to keep the E max, but I'm going to replace one of the E maxes with B max. Square root of epsilon mu naught. All right, notice this will cancel the product of those two, and we get that the average, I've lost a 2. Oh, there's the 2. There should still be the 2. So the average is just E max, B max, over 2 mu naught. I don't know why this is really any better than any of the other versions that you might have. There's really nothing wrong with this first version right here. So all three of those expressions are equivalent, and all three of those expressions give you an average energy density. And the unit, of course, no matter which one you use, is going to be the number of watts per meter squared. Let's look at an example. Suppose that we've got a laser cutter and it has a maximum energy electric field of 2.76 times 10 to the 5th volts per meter over an area of 2 square millimeters. So basically 2 square millimeters, it's really little, but picture a laser, small little red laser, oops, I meant to change colors, doesn't have to be red, but red, shining on this much area. That's not really 2 square millimeters, but you get the idea. With that maximum energy field, let's find a lot of things. First question they ask us to find is Bmax. Well, if I know Emax, I know Bmax. Bmax is simply Emax divided by C because they're related by C. So if I put 2.76 times 10 to the 5th volts per meter, I divide that by 3 times 10 to the 8th meters per second, and I'm going to get 9.20 times 10 to the negative 4 Tesla. We could play around with those units and we could prove that volts per meter divided by meters per second is Tesla, but you're going to take my word because we've used that relationship more than once. The second thing they ask us to find is the maximum energy density. Well, the maximum energy density is epsilon naught E squared. So if we want the maximum, then we use the maximum value of the electric field. Epsilon is 8.85 times 10 to the negative 12. This was 2.76 times 10 to the 5th squared. Just doing an order, just to estimate, if I square 10 to the 5th, I get 10 to the 10th. This is 10 to the negative 12. I think I get something on the order of 10 to the negative 12. This is a roughly 9 times 3. It's going to be somewhere around 20. No, it's going to be a little smaller than 20 because I forgot to square this. 2.76 times 2.76 times 8.84. It's going to get a little bigger. It comes out to 0.674 joules per cubic meter. The intensity. Is this an average intensity? I believe this is going to be an average intensity. Is going to be, we can pick one of our average intensity formulas. I'm going to say it's Emax, Bmax over 2 mu naught. That is going to be 2.76 times 10 to the 5th, 9.20 times 10 to the negative 4, and then 2 times 4 pi times 10 to the negative 7. Get a calculator and type this in. 2.76 times 10 to the 5th times 9.20 times 10 to the negative 4 divided by and I get 1.01 times 10 to the 8 watts per meter squared. And finally for D, they ask us to find what the power equals. Well, remember, power is watts. Intensity is the power per divided by the area. So our power is the intensity times the area. We're going to have to change our area of 2 square millimeters. That shouldn't be too hard. Our intensity is 1.01 times 10 to the 8th watts per meter squared. Our area, of course, was given to us as 2 square millimeters. I know there is 1 meter is 1,000 millimeters. I'm going to need to square that. So if we put that in our calculator, it comes out to be 202 watts. All right, that concludes the problems dealing with energy density, intensity, power. There is a discussion in the book about radiation pressure, and we're not going to deal with radiation pressure, so I just want you to be aware when you're reading. You'll probably want to read about energy density and intensity and power, but not necessarily about that section over radiation pressure. Okay. I also want to go over chapter 23, section 6. And it's about the nature of light. And the nature of light is really confusing. Before Isaac Newton's time, the general accepted theory is that light was particles. So I'm going to say roughly, and these are approximate because there's some overlap, but before roughly 1700, the general theory was light was a stream of particles. We call those particles corpuscles. I don't know that any of you would have ever heard this term, but back when I was a, say, middle school or high school student, when we studied, talked about blood, we didn't have red and white blood cells. We called them red and white corpuscles that were in your blood instead of blood cells. It's just a word that means particle. But around the latter part of the 1600s, 1665, all of a sudden we started getting wave properties. So I'm just going to say, after that, or let's say around 1665, scientists started to observe wave properties. Light does things that waves do, like refract and reflect. These are all wave properties. So then the convention was, obviously light has to be a wave. And that worked really well until around 1905, when Einstein used photons. Photons comes, that photo is the word for light, which are little bundles of energy. To explain the photoelectric effect. I think we're going to do a lab on the photoelectric effect. I'm not sure. So we've gone from light as a stream of particles to no weight. Light is a wave. Look at all these wave properties it has. Back to, oh yeah, but waves won't explain the photoelectric effect. If I'm going to explain the photoelectric effect, then I need to use the idea of light as particles or photons. And it really got confusing. But in 1930, quantum mechanics reconciled all this with the dual nature of light. Light has wave-particle duality. You really cannot understand light if you try to think of it exclusively as particles. It doesn't work. If you try to think of it exclusively as waves, it does not work. Now, where does light come from? We create light when we switch on a light bulb, but what's going on? Well, the fundamental source, the root cause of all electromagnetic radiation is electric charge in accelerated motion. All objects emit radiation as a result of the thermal motion of their molecules. Everything's made up of these vibrating molecules, and these vibrating molecules emit heat. At a high enough a temperature, matter will emit enough visible light to be self-luminous. If you light something on fire, eventually it gets hot enough, think of charcoal, that it will glow red and then maybe even glow white if it's hot enough. Hot matter, lighting a candle, burning of logs, that's one source of light that we're familiar with. We also get a lot of our light during electrical discharges through ionized gases. Those are things like your neon light. We're not going to go into great depth at this point about how to actually create light, but you should know that all light is basically due to electric charge in accelerated motion. All right. The next section we go into is called geometric optics. And to do geometric optics, it helps to think of light not so much as a wave or a particle, but as a ray, a straight line. If you consider some light source, and maybe this is a light bulb, and maybe this is the sun, it emits light in all directions. You can think of it as emitting just like sound waves, where you have, let these lines represent the crest of the waves. If this is from crest to crest, then these would be wavelengths, and they'd be going out in a three-dimensional way in every direction. You could draw lines, rays that are perpendicular to those crests. And these would go out in every direction. These lines that I'm drawing that are perpendicular to the crest or to the wavefronts are called rays. So this would be a ray, and this would be a wavefront. And they are always going to be perpendicular to each other. Now, if you have a situation where your wavefronts are parallel, suppose we have a wave traveling this way. So here's our wavefronts, they're equally spaced. In that case, our rays would also be parallel to one another. And parallel rays are really useful for looking at geometric optics, which is where we're going. Geometric optics is how we explain how mirrors work and how lenses work. You say, well, where do you get a source of parallel rays? Because if I light a candle, it goes out in all directions. Well, one of the places that we can get parallel rays is from the sun. And you go, well, Miss Hughes, the sun spreads light out in all directions. And that's true. But let's draw a picture of the sun. Here is the sun. And way over here is the earth. Even though the sun is sending light out in all directions, the sunlight that actually reaches the earth is pretty much all coming from the same direction, because the earth is teeny-tiny, I'd really probably too much. For all practical purposes, the rays coming from the sun are all parallel. Okay, so that's one place we can get parallel rays. All right, I would recommend reading section 23.6. I just kind of touched on the highlights. It's not a section that requires mathematics. It's just some ideas to help you get acquainted by how we think about light. That's a good place to stop for now.